What's that? Not today.
How do you get like the Funko Pop things to have the cool backgrounds?
Yeah, the cool background.
I think mine was just a funky background.
You guys are just laying. They put as much effort into it.
I don't know, man. I don't know, but make sure my guy wasn't wearing shoes.
I love Steve's shoes. How like taped up they are.
Yeah,
Big fan of that.
they're good.
I finished this whole book of notes. Yeah. I know. So now I'm already on the second. All right, guys, 12:30. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for the impending weekend. Pray that you would help us to accomplish all the things that we need to get done, that you would help us to just just make it through, Lord. Help us to keep working, keep striving, and keep being successful. In your name we pray. Amen. Okay. Excellent, excellent. What we got going on? All right. So what are we doing today? What are we doing today? Let's recap last class. And then, before we do that, I've got to do this. All right, so we're going to recap last class. Right, we talked about state space. So let's watch this video as a form of recap.
In this video, I'm going to introduce state space equations, the model representation of choice for modern control. However, before we begin, a quick warning. We're not going to go into depth on the mathematics of state space. After this video, you're probably not going to be able to write out the equations for any arbitrary system. But what I think you will get is a good intuitive understanding of these equations, which can be a foundation that you can build on as you learn more. At the very least, it might clear up a few lingering questions you might have. So with that in mind, let's get to it. I'm Brian, and welcome to a MATLAB Tech Talk. I think an interesting thing about dynamic systems is that they can be represented by ordinary differential equations. This is because they have this property that how the system is changing at any given time is a function of its current state. If we zip through the derivation for a spring mass system real quick, you can see we end up with a differential equation. Now, the way that the system is changing, acceleration, is a function of the current state, position. If this dynamic system was initialized with some energy, it would continue to move on its own because of this relationship between the derivative of the state and the state itself. Think about initializing the system by stretching the spring and letting it go. Acceleration changes velocity, which changes position, and then that changes acceleration again. And it's going to oscillate back and forth without you having to add any external inputs. Since there's no damping in this system, the energy is conserved, and this acceleration, velocity, position cycle will continue forever. For any arbitrary dynamic system, if we look at how the energy changes by analyzing the relationship between its states and their derivatives, we can make claims about things like the stability of the system. Is the energy being dissipated over time? Then the system is stable, and the faster the energy is dissipated, the more stable it is. If the energy is growing unbounded over time, even for just a part of it, then the system as a whole is unstable. Stability is an inherent property of a system simply from the way that the states and their derivatives are connected to each other. The way the system moves, however, can also be influenced by external energy being added or removed over time. So the derivatives of a dynamic system are a function of both the current state as well as any external inputs. And state space representation is simply a repackaging of the high-order differential equations into a set of first-order differential equations that focus on this relationship. This repackaging can make the system easier to analyze because we can look at the underlying behavior of the interconnected system as well as how the system is affected by external inputs, even multiple external inputs, which is really powerful. There are also a lot of control techniques that are built on state space models, like Kalman filtering, LQR control, robust control, and model predictive control, to just name a few. There are also numerical solution benefits when simulating your system as a state space model, since you build the vector of the derivatives first and then integrate the whole vector to get the states. So all in all, they're pretty awesome and worth learning. Now let's take a moment to look at the state space equations in more detail and try to make a little sense of them. For this, we'll focus on the continuous form for a linear time invariant system. There are two equations. The first one is the state equation, which we've already developed a little intuition around, and the second equation is the output equation, which I'll get to in just a bit. State space representation is built around the state vector x. This is a vector of all of the state variables. And how the state vector changes, or the derivative of the state vector, is a linear combination of the current state plus a linear combination of the external inputs. In this way, we're not trying to look at the entire dynamics of the system end to end like we would with a high-order differential equation or a transfer function, but rather focus on the dynamics of each state variable and how those variables relate to each other. How does the first state change as a function of all of the states and all of the inputs? How does the second state change as a function of all of the states and inputs, and so on? And since we're only ever looking at the first derivative of each state, we end up with a set of first-order differential equations. What we're left with is a system of linear equations that we can package into matrix form. And if linear algebra is good for anything, it's definitely solving a system of linear equations. It is this repackaging into matrix form that gives us access to a lot of mathematical tools that we didn't have before. The matrix form of the state equation has two matrices, A and B. The A matrix describes how the internal states are all connected to each other, the underlying dynamics of the system. And the B matrix describes how the inputs enter into the system, which states are they affecting. Now let's look at the output equation. Y is a vector of the outputs of the system, or the part that you're interested in knowing. The important thing to realize is that the outputs are not necessarily the state variables. The C matrix describes how the states are combined to get the outputs, and the D matrix is used to allow the inputs to bypass the system altogether and feed forward to the output. A real simple example of the D matrix in action would be the state space representation of a simple multiplier, a gain block. The output equals the input times the gain, so in this way the A, B, and C matrices are all zero, since there are no derivatives and no states, and the D matrix is the value of the gain. Now, the importance of the output equation will become obvious when we start feeding back the outputs to develop a closed-loop controller for our system. But for now, it's enough to understand the structure of the equation, and in the next video on feedback control, we'll go into more depth on the relationship between the output and state equations. As you might have noticed, the state variables are the key to the whole thing. They show up in three places and are the part of the representation that I think is the hardest to conceptualize. Therefore, understanding what they are is really important. The state variables are the minimum set of variables that fully describe the system. Fully described means that we have enough information about the changing part of the system, or the variable part, that we can predict the system's future behavior. This will make more sense if we go back to the spring mass system and suss out what the state variables are by starting with no information about the system. If I draw the spring in mass like this and asked you to predict where the system will be in 1 second, what information would you need? Well, you'd want to know the system constants, like the spring constant and mass, and we'd want to know what the external force is that's acting on the mass, so the inputs. But this only tells you part of the story because you don't know what you might call the initial conditions for the variable parts of the system. Is the mass currently moving, and how hard is the spring pulling on the mass? Now, if we knew these two starting conditions, along with the system constants and inputs, then we would be able to predict where the mass would be after 1 second. So let's consider the first question. Is the mass currently moving? We would know this from the velocity of the mass, and velocity is variable since the mass would be oscillating back and forth, assuming there was some energy in the system. So we need velocity in order to predict the future position, so we can say that velocity is a state variable. It's necessary. Now let's turn to the initial spring force. Force is also a variable, but let's think about how we would derive it. It's the spring constant times the distance that the spring is stretched. So if we have that distance, or the position of the mass relative to the unstretched length of spring, then we would be able to get spring force. So the minimum number of variables we need to fully describe this system is 2, position and velocity. And since there are 2, this is a second-order system. So a natural question now might be, why not more states? Why not 3? Well, to answer that, let's consider acceleration. It's a variable since it's changing along with position and velocity. However, we don't need to know acceleration to fully describe the system. Acceleration is a result of force acting on a mass, and force in this case is a byproduct of the position of the mass. Therefore, we get acceleration through position, and adding acceleration to your list of state variables is just extra information. Now, something that might seem strange at first is that if we add a damper into the system, we're not increasing the order of the system, because we don't need any additional state variables to account for this additional element. The force from the damper is determined by the velocity of the mass, which, again, we already have in our state variable list. So both of these systems have the same number of state variables, 2. Now, a way you can verify that you have the right number of states needed to describe a system is to count the energy storage devices that your system has. Now, I'm not going to go into too much detail here because I think Dr. Rick Hill has done a great job of explaining it in his YouTube video that I've linked in the description below. But the general idea is this. A dynamic system stores energy in various ways. In our spring mass system, there's 2 energy storage elements. The spring, which stores potential energy, and the mass, which stores kinetic energy. The dynamic system moves and changes on its own simply because the energy that exists within the system transfers back and forth between storage elements and eventually dissipates through heat, which is ultimately lost to the environment. At any given time, if we know how much energy is stored in each element, then we know its state and have the information needed to fully understand the state of the system. Now, the states don't represent the energy directly, they're just needed to determine the energy. For the spring mass system, we know the energy in the mass from the velocity of the mass, and we know the energy in the spring from the position, or how far the spring is stretched. And if we know how those energies are connected within the system, or another way of putting it, how each state absorbs and loses energy based on the current state of the system, then we fully understand the system itself. And this is essentially what state space representation is doing for us. It's looking at the state variables, how the energy is stored, and combining them according to how energy is transferred between states and adding in any additional energy from the external sources. And with a few special caveats that Professor Hill describes, that is why the number of energy storage elements in your system equals the number of states. So our spring mass damper is still a second order system, since a damper doesn't store energy, it just dissipates it. So we know the order has to be 2, but why not 2 different states? Why position and velocity? Well, they don't have to be, and here's where things can get a little confusing. The state variables, position and velocity, can be thought of as coordinate systems within a state space. Go over 5 position units and up 3 velocity units. This point in the state space is the current state of the system, and the state vector describes that location. But we can describe this location in the state space with any 2 linearly independent variables, some arbitrary state 1 and state 2. We're going to end up with the same system state in the end. It's the same energy, just with different coordinates. And we do this redefining of state variables all the time with state space representation. That's what we're doing, for example, when we diagonalize the A matrix to get it into so-called modal form. These 2 models represent the exact same system. We've just chosen a different set of coordinates, a different basis for our state vector. So state vector x is made up of position and velocity, and state vector z is made up of 2 modal states, and these particular states change as a function of just themselves. That is, state 1 does not rely on the current value of state 2, and vice versa. And if we were able to write out the state space representation directly in modal form, then maybe we would. There's nothing really special about position and velocity for state variables, other than they are quantities that make intuitive sense to us. However, since the states are no longer defined as position and velocity, the C matrix needs to change if we want to keep the outputs position and velocity. In this way, we can see the benefit of the output equation. We're not forced to output the states exactly as we define them, but rather have the ability to linearly combine them into variables that we're interested in. Okay, that's where I'm going to leave this video for now. I hope this has helped you think about the state space equations in a slightly different way. Rather than thinking of them as a set of matrices that repackage the model into arbitrary first-order differential equations, we can think about them as writing out the dynamics for each state variable separately. And the dynamics are tied to how energy is stored and transferred within the system. By doing this, we get the benefit of being able to understand how these internal states change and relate to each other, how the energy is moving around, and we get to use the powerful tools in linear algebra to analyze and solve the equations. Now, MATLAB and Simulink are great environments to work with state space systems. You can convert to state space from a transfer function, manipulate the matrices, simulate them, and design and analyze control systems using a number of built-in tools. And I'm going to be using MATLAB to demonstrate control techniques with state space equations for the rest of this series. So if you're not familiar with using state space in MATLAB, or if you're looking for a quick refresher, I've linked a few videos in the description that are worth checking out. In the next video in this series, I'll go through the design of a simple feedback control system using state space representation.
All right. Cool. So state space, right? That's what we've been talking about. Figured that was a good way to recap rather than me run through it again, right? So USSR, what they used to call United Soviet Socialist Republic. You're a big fan of Rocky movies, right? Rocky 4, Ivan Drago, US. Okay. Great. Glad we cleared that up. Math and algebra, dang. I don't have time to cover all of math and all of algebra. That's a whole other class. It's a whole other series of classes. If you're feeling rusty on algebra, you need to get de-rusted. And so if you have any algebra questions, concerns, office hours is a great time to fill those up. Lab. Well, we haven't done a lab in a while. We're going to do another lab soon. Is there any specific question about the lab? Okay. Well, fantastic. All right. So everybody's feeling pretty good then, I guess. All right, here's the things to do. Now, so there's going to be some changes that aren't reflected on here, and I'm going to change some things. I'm going to change some things in LoudCloud, and next week you'll see them up here. But just so you guys are aware, homework 1 still going to be due the 8th. Lab 2 will be due the 15th. Exam 2 is not going to be the 19th anymore. I looked at the calendar, and covering a lecture the day before everyone leaves for Thanksgiving sounds like a great idea, but I don't feel like giving the same lecture the day that you guys come back from Thanksgiving. So we're just going to we're going to have the exam that day. So Tuesday before Thanksgiving will be the exam. Okay, that's going to be the 24th. Okay, Tuesday the 24th. And then homework 5 will still be due on the 22nd. And so we'll do before the exam. Okay. That way you guys get solutions for homework 5 too before the exam, right? So you can use it to study, maybe. If you're into studying and doing that sort of thing. Does have any questions on what's coming up? All right. Again, I will make those corrections in LoudCloud, right? And yeah, Taylor, Tuesday the 24th. I will make those corrections in LoudCloud, so it'll be reflected in there, and then all the rest of the slides for the rest of the semester will have the right dates on. We can't push the exam back any further than that because when you guys come back from Thanksgiving, we've got 3 weeks left in the semester, and we're going to devote all that time to frequency response analysis. Okay? That being said, we had our participation problem, which you guys hopefully turned in prior to class. We had to derive a mathematical model, and then we had to determine whether the equation needed to be left as state variable form or put into state space. You guys just needed to put them in LoudCloud, like private message. That was the deal. So there's that. So what do we do for this? Right? What do we do? No, thank you. So my question is, before we do the model, because we can do this model. This is the model we've done a few times before. This is spring mass damping. Do we need to put this all the way into state space, or do we leave it as state variable? State variable, says Trevor. Who agrees with Trevor?
I do.
A lot of people. Does anybody think that it's state space?
No.
Thanks, Taylor. And it's not state space. Right? Why? Because the requisite for being in state space is that you need to be linear, right? If your system is nonlinear, you cannot progress past state variable form. Later today, after we do a couple of examples, we will see how we can linearize systems, and then there's no more excuses for just leaving them as nonlinear. Okay. So how do we do it? Let's start with our diagram, right? Start with our diagram. We got a mass. I've got a force. I've got some spring force, and I've got some damper. And that's it. You're gonna start to see why the book uses Z as their positional notation. because I'm going to do a problem later where I don't use z, and it becomes very confusing when I transfer two state variables, right? Because x1 is equal to x, but x2 is also equal to x dot, right? Like it's confusing. So we're trying to use z for translation just so that it's a little bit clearer as to what is the state variable and what is not. You can use whatever you like. It doesn't matter. Just try not to get confused, right? Try not to get confused. What about inputs and outputs? What do I got on this? Yep. FA is the input. Say that the position is the output. All right, I give this some force and I produce some movement. All right, so we write down our mathematical truths. All right. And we're given this spring equation for a nonlinear spring. And we have this. Plus. Those are all the truths that we need to do this. So where do we go from here? Right? We go from we're going to sum our forces. Right, we're going to do a reduction, standard reduction process. Right, just because it's nonlinear doesn't mean we can't run through our steps. Right, so I've got my force in A minus my spring force minus my damper force is equal to mz double dot. Rearrange this, make some substitutions. I don't have this. What order system am I dealing with here? Second. Why? Because if you're looking at this beautiful model equation that we have, right, it's the highest order derivative is second. What if I had a circuit attached to this? What if this was an electromechanical system, right? You would have to add the order of the electrical system to the order of the mechanical system, right? They add. All right, so we know that this is second order model. What if you didn't remember that, right? What if you're like, oh, I don't really know how to do it? Remember the video, right? Video, got your energy storage. You've got a spring and you've got a mass. A mass can store some energy, right? Potential and kinetic energy. Spring can store potential energy. So we've got two energy storages in this system. Okay. So we need to define our state variables, right? So what are we going to choose as state variables for this? What was that, no? So what do we put in our x1 and x2? So, right, so z and z dots, and z dot and z double dot. Now, again, this is basically the same system that we saw in our video just now, right? It's just that we have a nonlinear spring. That's the only difference. So it's still second order. We still need two state variables. Remember, that's the significance of order when it comes to state space, right? The order that you have is the number of state variables that you need. Right? According to the video and according to what I said last class, right, we can choose whatever we want as state variables, right? It doesn't really matter. It's just that certain quantities make more sense from a physical standpoint than others, right? Certain make more sense than others. All right. So we've got this, right? What else do we need? Well, we also need our input, right? We'll call that U, and that'll be F of that. So now we can start to build some of these equations, right? I'm going to do that on the next slide because I'll leave this up for a second while I recopy my state variables. Right, so what is the point, right? What is the point here? Well, we're trying to make a series of coupled first order. Well, that wasn't supposed to happen. Something happened. No, thank you. Oh, I don't know, guys. I am confusion right now. I apologize. Something happened. Can you guys see my screen at all or no? Nope, you cannot.
No.
What in the world is this right here? Technical difficulties. Please stand by. Your call is important to us and will be answered in the order in which it was received. All right. So here we are. Let's try this again. All right. So here's just rewriting my state variables, right? So they're on the same page where we're getting these things together. So what do we know? Well, I know that x dot 1 is equal to z dot, right? That's also equal to x2, right? So we have our first equation. Remember, what we're trying to do with state variable format is we're trying to find a function of x dot has to be a function of some combination of my inputs, right? And or my state variables and my input, right? That's what we're trying to make. We also have that x dot 2 is equal to z double dot, right? Well, I'm going to go back. I'll go back a slide for a second. Because I don't want to skip this part of the math, right? So let's take this down here. I need to solve this for the highest order differential, right? So if I solve this for z double dot, this is going to equal 1 over m times negative b z dot minus k z minus k k1z minus k3 z cubed plus fa, right? Why is it important to do that? Well, remember, x dot 2 is equal to z double dot, right? And I need an equation that has x dot 2 is equal to a bunch of stuff that is in terms of my state variables and my inputs, right? So we can say, well, we just figured this out, right? We just figured that out. So I can plug in my state variables now, right? That shouldn't be a dot. No, that is, sorry. X1 minus K3 X1 cubed minus B X2. These are over M plus 1 over M times the cube. And like we said at the beginning of class, we just leave it like this because you cannot put this in state space in the current format. Right? Later, today, we'll talk about how we can linearize functions. Right? We can linearize functions, but right now, we're just going to leave it. Any questions on this one? No? We're feeling all right? That's it. Let's try another one. So we're going to derive. So the idea here is we're going to run through models of things that we've already done, right? Because we know how to make the model, and then we're going to put it in state space, right? So we're going to build on things that we've already done and try to learn from that, right? So here we've got our standard solenoid, right? So we're going to have some RL circuit, right? That's part of it. And that's going to exert an electromechanical force, right? And then we'll deal with that. Okay. So let's draw our diagram, right? We'll start with the circuit. That's not all. Oh man, Dr. D is not with it right now. Tell you what. Okay. I got some currents, and I've got my KVL loop here, right? KVL. Also have a free body diagram. And that's it. That's what we got. We're not doing anything tricky. We're not doing any dry friction. We don't have a damper. This is it. It's just straight up this. Okay. So in terms of inputs and outputs, right? What do we have? My input is going to be E in, right, for my circuit, and that's going to kick out I sub L, which is going to generate some FEM, which is going to provide my distance X. Right? So FEM is just a function of IL, right? Remember, it's just B times L times I sub L. Right, so let's reduce this now here. Oh, I'm sorry, or truths. Jumping ahead. For the circuit, we got that. This. Oh my gosh. Sorry, guys. It's not KB. Right. I've got KVL. For the mechanical system, I've got the sum of my forces is equal to mx double dot. I've got my spring force is kx, and I've got the electromagnetic force is equal to B times L times I sub L. All right, so electromagnetic force is dependent on the field strength, the amount of wire that I have, and the current that's being stored in the inductor. That's it. We should be good to go. So let's start with the circuit, right? We've done an RL circuit a few times. Start with KVL. And KVL told me that ER plus EL plus plus EB. Right? So that's it. That's the model. It's done. Right? We have that. Remember, it doesn't matter which side you put KB on, right? It's just doesn't matter what side you put that back EMF on, really. Especially if your end goal is to make state space, right? Because you're going to have to rearrange everything in terms of the highest order differential in each of your equations anyway. Okay. What order model is this circuit? first. So n equals 1. For the mechanical system, right, I'm going to sum my forces. Well, I've got FEM minus FK is equal to mx double dot. What order is the mechanical system? Second. So overall, what order is my system as a whole, both parts together? Third, right? So if it's a total, a third order system, how many state variables am I going to need? Third, right? So let's define some state variables, right? Define some state variables since we need 3. What do you guys think? What should we have as state variables?
X.
No? That sounds pretty good. X, sorry, not X dot there. That'd be weird. X and X dot and I sub L. How'd you come up with those? No?
Those are the three outputs that we normally use.
So you said that those are the 3 outputs that we normally use. And yeah, I mean, they're the dynamic variables, right? Remember in class on Tuesday when we started talking about this, right? We said that often these state variables are synonymous with the dynamic variables that we would use. Another way of thinking about this is you have a second order mechanical system. So you need 2 state variables to talk about the mechanical system. And you have a first order electrical system. So you need one that's in terms of your electrical system. Right, so that's where the split comes from. Right, that's how we have to deal with that. The other way that we can think about choosing state variables is based on the energy storage that you have. Right? The spring stores energy based off of position. The mass stores energy based off of velocity, right? 1/2 mv squared. And the inductor stores energy based off of the current, right? 1/2 L I dot L squared. 1/2 L I L squared. All right, so that's where we get these. That's another way that we can come up with these. Or you can pick other things that don't have any physical meaning like they showed in the video, right? But we're going to stick to things that actually have physical meaning because they're a little bit more intuitive for us, right? Cool. So before I go to the next slide, because I don't want to have to come back, let's solve, well, no, we'll just do it on the next one. We're going to have to solve both of these equations for our highest order differential now, right? That's the next step. So we take our circuit, right? We had En is equal to RL or RIL plus Li dot L plus KIL X dot. Okay. So I'm going to write this in terms of I dot L. Let me write it in a better way. So something that looks like this. Why, doctor? Why not use X dot? Why use I dot L? It's a good question. Right? This is the only place where we have I dot L defined. Right? This is the only place in our system of equations that we have I dot L defined. We need to have an equation for I dot L because it's in our state variable list. So when we go to state space, we have our x dot vector, right? If you don't have an equation for I dot L, you're just going to get zeros all the way across, right? It's not useful. The other reason is, if we go back to our list of state variables, we end up with this relationship again, right? Well, x dot 2 is equal to x3. So we already have an equation for x dot. We already have a first order differential equation for x dot in terms of our state variables. What about solving the mechanical system when we have to solve it for x double dot, right? It's going to be 1 over m times negative k x plus 2 l I sub l. Now we can put this in state variable format, right? Now we're just going to plug in our state variables for all of our, where they're applicable, right? Let's do that. Oh, sorry, that's x3. That's one x3. I wrote this in the most bizarre way possible. So let me rewrite it. Right? Because does it matter the order that you write it? No. But let's help ourselves out a little bit here, right? Oh. We're seeing an issue here. Right? At least I am. What are you doing? I realize it's not in a good order. Can we write this as a state space representation? Can we? How do you get x1 times x3? So we can't. Turns out. You can't write this as state space. How do you make a matrix that gives you x1 times x3? Remember, our setup is ax plus bu, x dot equal ax plus bu, right? You're not going to be able, the way that we have this defined, where x1 is a state variable, to multiply it by x3. So we would have to linearize this equation before we can put it in the state space. There's a trick. What if we left that as E sub b and didn't plug it in, right? Could we do it then? No, because then we'd have to define, well, yes, depends, right? If you define E sub b as an input or an output, then you could. But typically when we're dealing with state space, we're going to deal with systems as a whole, not as systems as a part. Okay? So state space is really nice because it will tell us everything about the entire system as a whole, right, when we solve it. And because it's a matrix equation, when we write our output equations, right, we can define multiple outputs and have them solve for all of them at once, which is nice. But the very specific caveat is that you need a linear system in order to use state space, right? Does anybody have any questions so far? Everybody doing all right? Stop asking me if I'm all right. You're making me feel like I'm not all right. Got it. By the way, I also have a computer over here so I can see everybody online. It's great. The Dr. D internet form. Well, if we don't have any questions, let's talk about linearization then, right? This is the lead up, right? Not all equations are linear. How do we make them linear? How do we bend them to our will? Create them, linear fast, right? Well, linearization is the method of converting a nonlinear equation into a linear equation, right? Relies on a Taylor series expansion about some reference point or a nominal point that we're going to call x star or u star, right? So there's some nominal state x star that we are trying to stick around, and there's some input u star that gets us to that state. Okay. Why do we want to linearize things? Well, we want to linearize things because then we can solve them, right? It's a lot easier to solve a linear equation than a nonlinear. Why? Well, there's a wealth of linear analysis tools, and there's no general unifying theory on solving nonlinear systems. Further, many systems, real-life systems, are highly nonlinear, such as hydraulic systems. So being able to linearize about an operating point, right, is pretty important. A linearized model is reasonably accurate and representative of the true nonlinear model as long as the dynamic variables don't stray too much from the operating. This is the whole idea of having small perturbations, right? Your model is good over a short distance, right? Model is good over a short distance. So visually, what are we trying to do? Well, let's look at this graphically. Well, I guess in a second. Not this second, the next second. First, let's go over a process. So first, we need to choose or solve for our normal or nominal operating point, right? In the real world, you'll know, right? For like a hydraulic system, you'll have a range of pressures that you need to operate over, right? So you can pick one that's in there and the model. So you need to figure out where you want to reference this system, right? The operating point could be given, it could be an equilibrium point, right? So that's the most common thing that we'll see is you'll have some steady state point, right? Other common choices are places of lowest energy in the system, right? So for example, for the inverted pendulum problem, right, we have two equilibrium points there. We have when it's all the way at the bottom and when it's all the way at the top, right? One of those is highly volatile. The other one is less so, more stable, right? But both of those are fine. So once we figure out where we want to operate around, we typically call this X star and U star. So if you see the star notation, this is telling you that we are at a nominal state or a nominal input. The nominal input is the input that is required to reach the nominal state. Okay, I want to make that clear as well. We then redefine our governing equations in terms of the nominal value variables and some perturbation around that point, right? So these models have a little bit of robustness to them, right? Some of them are better than others. Some of them are good over longer distances, right? We need to figure out how good they are, but we're going to operate under the idea that you're going to start at this operating point and then you're going to move around it a little bit, right? So you have this delta, right? This perturbation. And we can define that as delta x is equal to x minus x star, and delta u is equal to u minus u star. And then we're going to expand this new equation using the Taylor series and evaluating at our nominal value. And we're only going to keep the first order linear terms. We're only going to keep the first order linear terms. Why? Turns out that as we move through the Taylor series, the higher order terms have, yes, do they make our answer more accurate? Sure. But they don't add enough to it to warrant keeping them, right? They don't add enough to warrant keeping them. And in fact, when you look at the Taylor series, right, the second order term has a 1 is divided by half, right? Or 1 over 2 factorial. Third order term is 1 over 3 factorial, and so on, right? So they get smaller and smaller and smaller and smaller as we go. So we just tend to ignore anything beyond the first order term. Okay, graphically, here's the graphically part. Graphically, what are we doing? Well, if I have this nonlinear curve here, and I want to normalize it, or I want to linearize it about certain points, right? What am I actually trying to do? Well, I'm actually trying to make a line that is tangent to the curve at that point, that goes through that point, right? That's what I'm trying to do. Right? I'm trying to find this line where if A is 0, right? I want to find this line. I want to find this line B or this line C, okay? That's what I'm trying to find. So I'm picking a point on my curve, or I'm picking a point in my function, and I'm saying, I want to operate at this point. Let me see how good of a model I can get linearly here. Right now, see, here's the problem though. Right, here's the problem. The farther away that I get from my reference point, the more error I have in my model. And that's the problem. So what do we do? What do we do then? Well, then you pick another point and you chain those models together. You just basically chain a bunch of linear models together over and over again, right? Or, you know, if it's not fixable in a linear model, then you start looking at how can I incorporate these nonlinearities and actually use a numerical solver and do all those things, right? This is the general point, right? So the other thing here is that the line that you're creating has the same slope as the function, as the nonlinear function at the point, at the reference, right? That's why it's changed. So keep that in mind. Okay. It turns out that there's two ways that I want you guys to kind of think about this, okay? There's two ways that we can think about this. We'll go through the Taylor series representation first, and then we'll talk about another way that might be conceptually a little bit more palatable. So suppose we have this first order nonlinear system that has one input, okay? So you can, yeah, that's my x dot. My x dot tells me that it's a function of, my x dot's equal to a function of x and u, and we're told that it's nonlinear, right? So what do? Well, step one, the nominal input, u star, results in the nominal state x star, right? So I know that if I give this u star, I will get to x star, right? We're operating under that assumption. So that's my nominal point. So remember, find your nominal point, find your operating point, your reference point, whatever you want to call it. Step two, the perturbation variables are delta x is equal to x minus x star, and delta U is equal to U minus U star. And then we're going to rewrite the nonlinear equation in terms of my nominal perturbation variables, right? So I want you to take a look at this, right? If I start with x dot is equal to f, a function of x and u, well, look at this equation. If I rewrite this, let me get a good delta. And I rewrite this one, right? So I can rewrite this, I can plug these into this equation here, right? And so I'll get that this is a function of delta x plus x star and delta u plus u star. If I take the derivative of x, I end up with this, which is the equation that's underneath, right? So just showing you what's under the hood, right? How did we get from x and u to delta x plus x star and delta u plus u star, right? That's all. And then the third step is we take that equation and we expand it in a Taylor series expansion. Okay. So delta x dot plus x dot star is equal to some function of x star and u star plus the partial derivative of my function with respect to x evaluated at my nominal point times delta x plus all of my higher order terms, right? And we already said these are going to go away. We're not even going to consider these higher order terms. But I also have to do the same thing for my function. Take the partial of my function with respect to my input and evaluate it at the nominal point. And if I do these things, I will end up with the equation in the red box. End up with the equation in the red box. This is a linear model in terms of delta x and delta t. Remember what we're trying to do, though. We are just trying to make a line. We're trying to make a line that goes through a point. And so we're taking this nonlinear function, this nonlinear model, and we are finding a point that we want to operate at, and we're drawing a line to that point that's tangent to our curve, right? So what would df dx be? What is that function? What does this represent? What does df dx represent? It's the change of my function with respect to x. The change of my function with respect to x. What is that? What's another name for that when we're talking about lines? Slope. It's the slope of a line. It's the slope at the point, right? That's the derivative of our line at the point that we are interested in analyzing. So, all right. So another way of thinking about this, right? Another way of thinking about this is, we'll do it on the next slide, wherever. There's another way of thinking about this, right? This is just telling you that if you had a system of equations, you can do the same thing for a system, right? You do it, each equation that's nonlinear, you linearize it, and you can throw it into state space. If you throw it into state space as is, you'll get delta x dot out, and so you'll have to repurpose it, right? So, okay, let's go over this, and we'll talk about another way of thinking about linearization. So I've got two first order differential equations that are both nonlinear. What do? Well, I find my nominal points, right? And I do the same thing for steps 1 and 2, right? Take my perturbation variables, plug them in, right? And then I'm going to do my Taylor series expansion on each. And then it turns out after the Taylor series expansion, the resulting linearized system can be put into state space representation, which now looks like this. So if you have a linearized system, if you've linearized your system, you're actually not getting x dot out, you're getting delta x dot. So you would have to, in order to solve this for x, you're going to have to recombine it in this equation. Okay? Because x is just x star plus delta x. Okay? A in this case is the different slopes of my lines, right? With respect to my, I have the slope of my line with respect to state 1, slope of my line with respect to state 2. I have the slope of my second function with respect to state 1 and with respect to state 2. That's all well and good, right? But Dr. D, you said there's another way of thinking about this that might be easier for us to conceptualize as opposed to Taylor series expansion. And that's true. I did say that. Another way that you can think about this is, what are we trying to do? Right? We're trying to make a line through a point. You can treat this like point slope form and write the equation of a line. I'll show you what I'm talking about. Do an example. Hey, check this out. Everybody loves fluids, right? So let's do a fluids problem. Consider the relationship between pressure drop and volumetric flow. For turbulent flow through an orifice, hey, we're given the equation. Q is equal to KT square root of P. We're also given this plot of what this flow, what the volumetric flow versus pressure looks like, or pressure versus volumetric flow looks like. We can see the blue line. The blue lines are nonlinear model. And they're telling us, excuse me, they're telling us, but I really want you to normalize or linearize it about this point right here, right? That would be great if you could please linearize this model right there. Okay, we can do that. If we look at the graph, we can make some estimates, right? And I can say that Q star is roughly 2.39 times 10 to the minus fourth cubic meters per second. And P star is roughly 400 kilopascals. I could say that. Okay. Let's go back a couple slides and look at something. We're going to try this with the Taylor series expansion. So if I'm going to do a Taylor series expansion, right? So if I'm going to do this method, I found my nominal states. One is done. Did it. Now we have to rewrite our equation in terms of the perturbation variables, right? So Q is equal to KT root of P. Okay, so that's really going to be delta Q minus Q star, right? Or is it plus Q star? Is equal to KT square root of delta P plus P. So we can apply our Taylor series expansion here, right? Which is what we're going to do. If we do that, we'll get delta Q plus Q star was equal to some function that is Q star, right? Which means those are going to cancel. Plus the partial of Q with respect to P evaluated at the star times delta P. What happens if you take the partial of this function, partial of Q with respect to Q. Zero, right? Partial of KT with respect to P, well, none of that changes with Q, right? So it's like taking the derivative of a constant, which would just be zero. So the second part of this, where you need to take the partial with respect to Q, goes away because it's zero. So now this becomes our approximation here, right? And we can rewrite this as delta Q is equal, I'm going to rewrite this as dq dp evaluated at the star delta P, right? Okay. Okay. And I pose to you that this is the same as me writing this equation. For a system in which our output is constant with respect to our input, the partial of that part is zero, right? And we are left with something that is just point slope form of a line. So this green line can be, we can analyze this green line by talking about what do we need? We need the slope. We need to know how far away we are from our operating point in the y direction and how far away we are from our operating point in the x direction. That's what we need. If we go with our, right, delta Q is just Q minus Q star, right? We know what Q star is. What's dP or dq dp? Well, if I take the derivative of this function up here, right, that's kt times p to the half, right? So this is the derivative of that's going to be k sub t over 2 times the square root of p, right? Because p to the half, I'll pull the 1/2 in front, becomes p to the negative 1/2, right, which is just 1 over the square root of p. I can evaluate this at my nominal point, right? And this gets multiplied by p minus p star. So Q is equal to kt over the square root of p, 2 times the square root of p, evaluated at star, times p minus p star plus q star. And I will submit to you that this is the same as this equation. And q star is just the y-intercept of my line. Right? It's where it intersects the y-axis. X star is my reference point, right? I know we're at 400 kPa in the x. So I now have a function that, depending on where I am with x, with pressure in this case, depending on what nominal point I choose, right, I will have a linear equation for any point, right? And that's kind of where we're at. Again, right? If you don't like thinking about it like Taylor series, you can use point slope form. That is fine. Personally, I prefer to think of it graphically like making a line, right? So obviously, the further away we get, the higher the pressure is, right? The bigger the difference we get on this curve. Right? How do we know what is an acceptable amount of deviation? Right? How do we know? When do we say this model is garbage? Right? Well, that depends. Depends on your application, right? Certain applications need much higher accuracy. some, we can have a larger amount of slop, right? Typically, if we're within 10%, that's typically okay. Right? If you guys have taken enough engineering classes at this point to understand that everything that we do is an estimate at best, and that's why factors of safety exist, right? You guys have any questions? Yeah, Jesse.
So we're looking at like how close the model is to like what like the I guess ideal is. So it's only good for that like little portion.
Right.
And then like if we wanted to make like a model for like let's say that curve, would we use several different equations just at certain points? Or
So that's why we need to, so the question was, if the model is only good over a certain amount of room, right? How do we know when we need to shift where we're taking our model about, right? And that's why choice of operating point is user defined. If you know, most systems have a range of things, a range of operating conditions, right? And so in the real world, like this pressure system, right? Say this is, it's a nonlinear flow through an orifice, right? I know that that orifice is going to be, I know that my overall system runs at a certain amount of pressure, right? I know what the range of pressure drops I'm expecting to be in are, and so, it looks fair. This model looks fairly good between, like, it looks really good between 300 and 500 kPa, right? And so if you know that you're going to operate within those conditions, then you can have a very good idea of how things are going to work, right? If you knew your system was going to be running between 800 and 1,000 kPa, then you would probably pick a nominal point around 900 and then relinearize it there, right? The nominal point is very much about where do you think your operating conditions are going to be, what is this system being designed for, and how is it going to be used, right? So that's kind of where those come from. Cool. Any other questions? Okay. All right, then you guys can try one. Take like 15 minutes. You don't need to do all three. Why don't for you guys, let's like you to do this one. Theta is equal to pi over 3. So obtain the linear approximation for f of theta is equal to sine theta when theta is equal to pi over 3. So that's your reference. That's your nominal. You have 15 minutes. So roughly till about 2 o'clock. A little bit. Also, this would be a great time for me to tell you to make sure that your calculators are in radians. What's one is very wrong and not very wrong? All right, guys, that's been about 15 minutes. It's been about 15 minutes. Let's talk about it. Did anybody get anywhere that they'd be willing to share what they did? All right, I guess not, man. I'm guessing no. Nobody. All right. Let's just go over it anyway. All right, so we're gonna do a couple of things here, right? We're gonna do the pi over 3 solution, and I'm gonna show you the 0 solution because I want to show you guys something interesting that happens when we linearize sine of theta at 0. So how do we do this, right? Everybody that I talk to is having trouble even just getting started here, right? Because it's confusing, right? We're talking about Taylor series expansion, but then you said that it could just be like the slope of a line. And I don't know what's going on, right? And this is confusing me. Fair. It's okay to be confused. Let's talk about it. So I'm going to start off with my function, f of theta, right? F of theta is equal to sine theta. I'm also going to take the derivative of that, right? F prime of theta is cosine theta, right? And we're going to hang on to that for a second. Because remember, I did tell you that we could model this like this, right? Where B is just y star. Why? Why can we do this? Well, remember, the slope of a line is equal to the rise over the run, right? So we can use point slope form to figure out how to make this line. So I'm not even going to touch Taylor series. You're doing the same thing. It just makes it just complicates it a little bit in this case. All right, so here's what I've got, right? And I want to fit my equation into this. Well, this here, right, this derivative, that's just m, right? That's the slope of my line at that point, as long as I evaluate this at my nominal point, which for us is pi over 3. We'll get back to that in a second, right? So I'm looking for y, right? I'm looking for y, my y coordinate, right? And I know my slope is cosine theta. X, well, x star was just pi over 3. Y star is just sine, is just f of theta star, right? Which is 0.866. And there it is. There's my equation, my linearized equation. Watch what happens if you plug in pi over 3. And what happens if you plug in pi over 3 here? You get 0.866, right? What's sine of pi over 3? Right here. It's 0.866. So at the point that we are nominal at, we are perfect. We have a perfect model there, right? Why? Because the line intersects the curve there. What happens when we get further away? We'll talk about that in a second. We'll talk about that in a second, right? We'll talk about that in a second. What I want to do is I want to show you guys for theta is equal to 0. So we're going to do the same thing for theta equals to 0, right? Well, let me just rewrite this. This is actually 0.5 here, right? Cosine of pi over 3 is 0.5, just so we all know that. And so that's what it actually looks like. If I use this same format, right? I use this same format here and these equations up here. I've got what? Well, I'm going to have y is equal to the cosine of theta evaluated at star times x minus 0 plus the sine of 0 is 0, right? Okay. Cosine of 0 is 1. So it turns out the y is equal to x, but x is just what? theta. So you're telling me that the linear approximation of sine about 0 is theta? Never would have. I've never heard that before except in the lab and on the exam when you talk to us about it, and all the pendulum tolerance units, but we've just proven the small angle approximation. Right? We've just proven it. Does it work? Well, when you plug in 0, you get 0, which is theta, right? Okay. Let's test this out. Dr. G said this would work to 5 degrees, right? So, how are we going to test this, right? Well, if I use my approximation at 5 degrees, 5 degrees is how many radians? We'll call it 0.0873 radians. Right? So we're saying at 5 degrees, we're at 0.0873 radians. What is sine? The actual sine value, 0.0873. I'll just use the whole thing. Sine 0.0873 is 0.08715. And so 2. So yeah, looks like that's pretty close for 5 degrees, right? Looks like we're pretty close. That'll work. That'll work. If we go back and we look at our graph here, if we go back and we look at our graph, this looks like it's pretty good up to half a radian, right? Up to about half a radian. It's very close. Very close. So yeah. So we can create a linear model, right? It's just a line that passes through that point. Taylor series expansion works, and that's fine. Personally, I think it is conceptually easier to think about the fact that this is a line. It has to pass through this point, and we can use point slope form to figure out what that is, as long as we know the function that we're trying to linearize. It often helps to draw it out, right? Plot your function, put a line on it where you think it's supposed to be, right? Check it out. Remember, the farther away that we get from our reference point, the less accurate we are going to be. In certain cases, that's a long distance, right? Because we might have a function like the sine function that has a same slope for a very long period of time before it reverts, right? Or you could be at the very top of the sine function, right? And you have a flat line that's at the apex of one of the peaks, right? And you have a horizontal line that drops off horribly, right? So keep that in mind. This would be a very bad place for you to create a linear model, right? You're going to get a significant amount of drop off. Also, it's typically not the most stable in terms of, you're at the very peak. Okay. You guys have any questions? No? Nothing? Okay. We're not going to watch this video today. We'll watch it as a recap on Tuesday next week. I think that's going to serve us better. So let's talk about something that we are all very well versed in, right? Input-output equations. Exciting. We have been doing input-output equations for the past 5 weeks, right? Literally, that has been the only thing that I've been talking to you about is make sure that when you reduce your equations, they're in the You know, your inputs on one side and your outputs on the other. So why? Why do we care? Right? We're going to find out why we care. But first of all, let's consider this single input, single output system here. Right? I've got some input U that's coming in and some output Y that's coming out. This is general block diagram format. What's inside the block diagram box, right? What's inside the system box? Your equation, right? Your model for the system. This is how Simulink works, right? You put a block in, you feed it a signal, there's some plant in there, right? That's just a mathematical equation that is describing your system, and then you get some output out, right? The IO equation is a differential equation that involves the input variables and the output variables and their derivatives, right? Which is exactly what we've been doing, right? It's not different than anything we've been doing. What is different is the way that the book tells you to write it. And we'll get there in a second, right? Right there, what we have, that equation is the general form of an IO equation for an nth order system. If we have a system with M output variables, we will have MIO equations, right? So it has nothing to do with the amount of inputs you have. It has everything to do with how many outputs you have as part of your system. You need to have as many input-output equations as you have outputs, which is basically how we've been doing things, right? We just haven't said anything. So unlike state variable equations, we can solve each part of our system independently using an IO equation. We don't need to solve a system of coupled differential equations when using IO equations. We can actually solve them independently, which is nice, right? You don't have to run this full-scale simulation if you're only wanting, you know, the current from your motor, right? You can use your IO equation. That's good. That's helpful in certain situations. Let's talk about this in terms of an example, right? Our standard mass spring damper system that has some applied force on it, right? It's a one degree of freedom mechanical system. Mz double dot plus dz dot plus kz is equal to F of A. So we're going to define our inputs and our outputs. Right? Our output we're going to call Y, and we're going to say that that is Z. Right? So the displacement is our output. We're going to say that the input variable is U. Right? And then we're going to rewrite our equation in terms of our inputs and our outputs. Right? Well, it's already there. Yeah, I know. But the book likes it this way, and there's a benefit to this way. But personally, I don't like to write it this way. And if you guys are asked for an input-output equation, I am perfectly fine with you guys leaving it like this. There's a couple of reasons. The first is we're not doing any systems that are super high order, where you're going to get confused about which Z we're talking about, right? The other thing is, when you look at the top equation, you automatically know what the input is. You don't have to say, well, what was Y again? I'm not really sure what Y was, right? So if you leave it like we've been leaving it when you're asked for an input-output equation, that's perfectly fine. I'm not going to make you change midstream here. And honestly, when we get to transfer functions proper, I think this is a lot nicer because we can keep track of our inputs and our outputs directly instead of everything being Y and U. Okay. But now you've seen it, so when the book does it, right, you'll know that that's the thing that the book does. Since this equation involves only inputs and outputs, it's called an input-output equation. If you have multiple states and outputs that require, you're going to have to do significant algebra to put these, to derive input-output equations. And we've seen that a little bit. Nothing major right now. But if we end up with a system with multiple outputs, then you've got to really work that algebra. Let's talk about the differential operator. Why? Well, we'll find out why in a second. All right. So okay. For more complicated systems with multiple outputs, developing I/O equations involves much more effort than obtaining an SSR. So for higher order systems that have multiple inputs, multiple outputs, really complex systems, state space representation is where we want to live, right? But it's often useful to simplify our input output equations, right? So that we don't, it's often useful to simplify them and use algebra. And we can replace some of our things with this D operator. What is the D operator? Capital D is ddt. Okay, we're going to say that capital D is ddt. So I can take all my time derivatives, right, and I can replace them with D, right? So if D is equal to ddt, remember, y dot is equal to d dt of y, which is going to be equal to dy. Right, the second derivative, well, y double dot is equal to d squared dt squared y, which is going to be d squared y, and so on, right? So anytime we have a derivative, a time derivative, we can replace it with capital D. That's great, Dr. D. But why? Why should we even bother doing that? That seems like, I just don't understand, right? Yeah, sure. Turns out that we can use it to help us manipulate some of our differential equations. How? Excellent question. By talking about transfer functions. Now, we'll preface this by saying we will be going very in-depth into Laplace transforms in a couple of weeks. Right now, we are going to learn how to skirt Laplace transforms and use what is called a time domain transfer function. Later in the semester, we will learn how to make a proper transfer function from a Laplace transform, right, and why we can do that. But for right now, we're going to give a very high-level overview of Laplace transforms. So transfer function is convenient, as it is a nice way to represent and analyze their input and output relationships for a single input, single output dynamic system. They are based on Laplace transform methods, which we will go over ad nauseum. Right? Laplace transforms are an operation method that can be used to solve linear differential equations with nothing more than algebra. Okay? So you will be able to do algebra and solve linear ordinary differential equations. How it does it is it takes a function of time and it transforms it and puts it in something called the Laplace domain or the S domain. And how do we do that? Well, if I take the Laplace transform of a function f of t, right? Special, that nice script L is the Laplace transform of f of t. It then becomes capital F of s, which is just the integral from 0 to infinity of f of t e to the minus s times t dt. And that is the definition of a Laplace transform. And we will come back to that later in the semester, and we'll actually use it to create a Laplace transform by hand. We can use Laplace transformation to take standard time functions and put them in the Laplace domain. And by doing that, people have done this quite a bit. It turns out that if you take the Laplace transform of a function, it doesn't change the next time you take the Laplace transform of the same function. Laplace transform of sine of theta is always equal to the same thing. Who would have thought? Crazy. And so people put that in a table, and there's Laplace transform tables. And you can go on the Google, type Laplace transform table, and you get any one of millions of Laplace transform tables. You'll also be getting a Laplace transform table that I'll post for you that uses the most common ones that are seen in this class. Also, for one of the assignments later in the semester for participation, you'll have to complete one of the Laplace transform tables that are left blank, right? Because that's fun. Everybody loves, look, I know you guys on Saturday nights, you like to stay home and do your Laplace transform tables. And so I just thought that I would help you there. All right. why do we care about transfer functions? Well, programs like MATLAB and Simulink use transfer functions quite a bit, especially in block diagrams. They're nice ways of representing our differential equations, and they have the added benefit of making it a lot easier for us to solve for time domain responses by doing inverse Laplace transforms, which, as I've said before, just requires us to do algebra. Turns out, though, that we can sidestep the Laplace transform to create a transfer function. Right? And these are called time domain transfer functions. They're called time domain transfer functions. So in general, how do we develop a transfer function? Right? In general, so imagine for a second I've got this third order system here. Right? This third order differential equation. And I want to take the Laplace transform of it, but you just said that we're not, but I'm going to do it anyway. Right? We're going to go over it again later, right? But just bear with me here. I'm proving a point. So if you take the Laplace transform, and we consider an exponential input that we're going to call u of s e to the st, right? And it turns out that the Laplace domain, the S domain, is complex in nature, right? So it has real and imaginary parts, which is super fun. Not like imaginary like it doesn't exist, right? But imaginary like imaginary numbers, right? That imaginary, the fun kind of imaginary. Okay. So if we use the Euler identity, e to the j theta is equal to cosine theta plus j sine theta. Right? We're going to use j as our complex number, not I, but j. Then the exponential function that we're given turns into e to the sigma t plus cosine omega t plus j sine omega t. So therefore, e to the st will be a complex which has real and imaginary parts. And since the input is strictly real, u sub s will be the complex conjugate of e to the st. Great. That sounds like a bunch of mumbo jumbo, doesn't it? Sure does. Let's keep going. So what does this all mean, right? Well, it turns out that whether you have a differential equation in the Laplace domain or in the time domain, it's still a differential equation, and it will still have the same answer regardless of how you solve it, right? Because that's the whole point of doing this method, right? If there was a different answer, then why would we do it? So recall from differential equations that if the input u of t is equal to u of s e to the st, the particular solution will also be an exponential function, right? So this is saying what? That we need to remember that from differential equations, if we have an input that's an exponential, we should expect to get an exponential out, right? That's what this is saying. So we can substitute all of these things in using a little bit of Laplace transform magic that we don't know yet, right? Our Laplace transform sorcery. And what we get is this equation right here that I'm going to put a green box around so that we all know what I mean by when I say right here. This guy. This one. Right? So it turns out that when you take the Laplace transform of our original equation, you get a3s cubed plus a2. Well, wasn't that a3y triple dot? And that became s cubed? Wait a second. Yeah. That seems real similar to that d operator we were talking about earlier, doesn't it? We'll get there. Okay, so I get this input-output equation, right? And what I've done, what doing the Laplace transform has done, is allowed me to take everything that is a function of y and move all of my differentials and my coefficients into the parentheses, and then I just have y of x times e to the st, right? I can do the same thing for my input. The e to the st is canceled. It's on both sides, so it's gone. Now we can create our transfer function. What is the transfer function? It is the ratio of the system's output to the system's input. And notice what happens when we go from the green box to the red box. We have divided both sides by use of S on this green equation, and we've divided both sides by A, those A terms, right? I'm not going to say them all by the A terms, right? The left-hand side. And we're left with this. Y of S over U of S is equal to B1S plus B0 over A3S cubed plus A2S squared plus A1S plus A naught. And this is my transfer function, and we will say that this is equal to G of S because that's what we call our transfer function, is G of S or H of S, right? Sometimes, depending on what we're doing. So there's our transfer function. Great. We made it. We don't know what any of it means, but we did it, right? Well, there's an interesting consequence to making a transfer function. I won't say consequence. There's an interesting functionality here. If you wanted the solution to this equation, right? You want to know what the output is. How do you do it? Well, the output's Y of S, right? If I multiply my transfer function times my input, right? I get the output. It's in the Laplace space, but I get it. So can't we do this in the time domain and be able to just pull out our solution if we had a time domain transfer function? It's a good question. Turns out that we can develop a time domain transfer function. When we make it, we do a similar operation, right? Except there's less moving parts and we don't need a Laplace transform. We're going to take that D operator. I'm going to start with our equation here on the top. I'm going to plug in our D operator for all of our differentials, right? So I get A3D cubed times Y plus A2D squared times Y, all the way down, right? And then I can group everything, and I can take all of my Y's out, right? And I can isolate all of my coefficients. And I do the same thing for U. And then I can create a ratio of the output to the input. And look, I get my time domain transfer function. Hey, that looks a lot like the Laplace domain transfer function, except that it has D's instead of S's. Yes, it does. It looks a lot like that. We are not going to get into how to use transfer functions today. That is coming next week. Right? We'll talk more about that. They are really useful. The thing about transfer functions that I need to tell you. Transfer functions assume that you have zero initial conditions, right? Assumes that your initial conditions are zero. And so if you're asked to find a transfer function and you're given initial conditions, you are supposed to summarily ignore them and treat them as if they are zero. Okay. Transfer function is a very specific thing. The initial conditions of your system are zero when you're looking for a transfer function. Talk about why when we get to Laplace transforms. Here's some notes on transfer functions. All right, first, on the prior slide, we can simply interchange S and D symbols and produce transfer functions purely for the sake of representing dynamic systems. I want to stress to you that while MATLAB and Simulink very often rely on transfer functions, which use the complex variable S to represent the input-output differential equations, their numerical solution is based on a time domain differential equation and not the Laplace transform solution. So MATLAB on the back end, MATLAB is using a differential equation solver. It is not doing the inverse Laplace transform like we were going to do by hand. So I guess our bottom line is MATLAB is better than us because it actually does differential equations, whereas we are just going to use algebra and get to the same solution. 6 of one, half dozen of the other. Transfer functions are limited to LTI systems. If you do not have a linearly time invariant system, you cannot make a transfer function. Why? Because LTI systems are very specific. This is why we can say that B and K are constant, right? This is why, first of all, the linear portion of it is really important. Second of all, the time invariant portion of it means that our constants don't change with time, so we don't have to deal with partial differential equations. Right? This is something that we can use with ODEs. Transfer function is a mathematical model of a particular system's input-output equation. Okay? So it is not, the ratio of output to input is not the same for all systems, right? Each system has to be done differently. This is not something that we can tabulate. It is very dependent on the system that we're analyzing. The transfer function holds for any input and is unrelated to a particular input function. So it doesn't matter if I have a sine wave, doesn't matter if I have a ramp, a step, an impulse, whatever I happen to have, the transfer function doesn't care, right? Transfer function does not depend on what my input is. It only depends on the system as a whole, right? And finally, many different systems, right, whether they're mechanical, electrical, hydraulic, thermal, can have identical transfer functions. What happens if two systems have the same transfer function? You should expect that they have the same output for the same input, which makes them equivalent, right? Makes equivalent systems. Let's try one. All right, I want you guys take a couple minutes, take some time and derive the transfer function for this IO equation. Let's take a couple more minutes. We'll talk about it. Anybody wants more time? Everyone wants more time? It's still okay? What's going on? You guys are very quiet today. Just want to get done and get out of here. Yeah. All right. Let's talk about it then. So what do we do? I know a couple people feel good, feel like they did well on this one. So why doesn't somebody tell them, share with the class? Let me share with the class.
Like just share what we got.
Yeah. What'd you get?
I got YT over UT equals 40 over D squared plus 8D plus 10.
For those of you playing at home, Zach said that he got y of t over u of t is equal to 4d over d squared plus 8d plus 10, which is very much correct. Good work. All right, so how did we get there? All right, what do we have to do? We're going to substitute in the d operator, right? Remember, d is equal to d dt. So when we look at this, we've got d squared y plus 8dy plus 10y is equal to 4du. I can rewrite this in group. All right, I can pull out my y's there, and I'm left with this. But I need to create the ratio of y of t to u of t. In order to do that, I need to divide both sides by u, but also divide both sides by this. Oh man, hold on. Hold up. I got this. Surely I can copy something that I've written down before. Surely. Apparently not. Apparently I'm riding the struggle bus today, guys. I apologize. All right, so if we divide these things, right, these things and these things go in, I'm left with 4d over d squared plus 8d plus 10. Fun fact, he says, and no one believes him. Fun fact, the denominator of this transfer function is also known as the characteristic equation of our system. And maybe some of you are remembering, they said something about characteristic equations in diffie-Q, but then the pain and the rage blackouts happened, and I don't know what's going on anymore, right? Maybe you're thinking that, right? Well, yes, we'll talk about what that means, right? We'll talk about what that means. What if, remember, this also equals that, because the D and the S are interchangeable, right? So there, hey, I did a little posture. Great. Okay, let's try something else that's similar but different. What if I gave you a transfer function and asked you to give me the IO equation? What happens then? Dogs and cats living together, right? Pure anarchy. What happens then? Nobody knows. We go home. Okay, so I'm given this transfer function, right? Remember, this is the same as this. Okay. So you just do what we just did, but in reverse order. Right? We're just going to do what we just did, but in reverse order, right? So I'm going to multiply, cross multiply here, right? Cross multiply these things. I'll end up with 7d plus 4 times u of t is equal to 2d squared plus 10d plus 28 times y of t. And it's 7d u of t plus 4 u of t is equal to 2d squared y plus 10d y plus 28y. Get rid of my d operator. 7 u dot plus 4 u is equal to 2 y double dot plus 10 y dot plus 28 times y. Right? So it's just in reverse, right? Last time we started with the equation, we added the d operator, we grouped our terms, we divided. This time, we start with the transfer function, we cross multiply, we distribute our y's and our t's, our y's and our u's, right? Then we invert the process of using the d operator, right? So we can go back to having a differential equation. We should be able to go seamlessly back and forth from transfer function to ODE, right? That's the goal. That's the goal. You guys have any questions so far on transfer functions, any other linearization, anything else that we did today? No. Everybody's good. I'm gonna figure out a way to get a 3D camera. I'm gonna do it. Then everybody at home can watch with 3D glasses, and I can do stupid stuff. All right. Well, if nobody's got any more questions. Oh, apparently I'm signed out. Interesting, because I'm still in the meeting. And we'll do our deep thoughts from Dr. D for today. Okay, we'll do our end of the week stuff. This is very important things. These are things that keep me up at night. Is a hot dog a sandwich? Sure, absolutely not. Irrelevant. I'm getting tired of being subjected to your random thoughts. These are the things, brother. These are important questions that need to be answered. I mean, guys, it's only been 6 weeks, right? There's a whole other half plus 2 weeks of semester left here, right? So if you're already tired of it, I hate to tell you this, it's just going to keep coming. I mean, sure is like, we're pretty sure. I mean, if it makes you feel better, Jesse, sure can be taken as absolutely 100% compliance with
That
the.
was my stance. I was just.
Yeah. I'll have to revise it for next time. Sure. Man, you guys are much more decisive about this than the last class. Last class was like 50-50 split of between irrelevant and I'm getting tired of you. No, it was between hot dog and between sandwich and no sandwich. I mean, it's a tricky one, right? So I pose this question: if I had two pieces of pizza and I put them on top of each other, is that a sandwich? Yeah, yeah, right. It's also delicious. Somebody said, well, hot dog isn't a sandwich because the bread isn't split. So that makes it not a sandwich because a sandwich has to have two. But then I said, what happens with sub sandwiches, right? What about hoagies, right? Or grinders or whatever they're called in your neck of the woods from wherever you grew up, right? Subs, man. As Trevor said, is a taco a sandwich, right? It's true. That's what you said. He said, is a hot dog a taco? I mean, I feel like it's pretty close. Would you put a hot dog in a taco shell, a hard, crispy taco shell? Would you? That's how my kids eat them. Yeah. Apparently, hot dogs are high choking hazards. But anyway, all right. How we feeling? Nah. Pretty solid middle of the road. If you're not feeling good, please come to office hours. Please come talk to me about it. Right? I can't help you if you don't let me know that you need help. Okay? So please come talk to me. And that's it. That's it for week 6, guys. Have a great weekend. Try to do something that's not school related. Yeah.
We learned that capital V represents derivative, so should we be
Oh man, nailed it, Justin. Just so you guys are aware, next week we're gonna start block diagrams. So you might want to bring your computer. Might want to bring your. I mean, Jesse, it does make sense. I make you do all the circuit problems as derivatives, not integrals. I mean, I can see where you would be going with this.
I have my capstone meeting, that's why I was
Sure. Not at all.
it's a little bit easier when like we're online on Tuesday, then like I can kind of have my Zooms going at the same time.
Sure.
So
Okay.
I
That's
just want
fine.
to let you know that's.
No, yeah, you told me. I think you told me last week.
Yeah, I just want to make sure like we're on the same page.
Okay.
It's not like, oh, you showed up late again.
No, it's cool. It's
All
fine.
right, thank you.
Make sure you get notes from the beginning. I don't think we did anything really important before you got here, but get notes from the beginning of class.
I honestly couldn't understand what you were
Sorry, I said make sure you get notes from the beginning of class.
Okay.
I don't think we did anything groundbreaking, but just make sure you check out the videos and stuff.
Okay.
Right.
Thank you.
Yep. Mm.
Goodbye.
Take it easy, Taylor.